An application of reduced row echelon form is finding the solution to a system of linear equations. The process is called Gauss-Jordan reduction method. So let us start by considering a system of m linear equations in n unknowns. So consider the following system of m linear equations in n unknowns. A sub 1 1 x1 plus a sub 1 2 x2 plus a sub 1 3 x3 plus a sub 1 n x sub n equal to a sub 1. A sub 2 1 x1, a sub 2 2 x2, a sub 2 3 x3 plus and so on and so forth, a sub 2n xn equal to a sub 2. Until the m equations, a sub m1 x1, a sub m2 x2, a sub m3 x3 plus and so on and so forth, a sub mn xn equal to b sub m. Let us now define the following matrices. Our matrix A is the m by n matrix consisting of the coefficients of all the unknowns a11, a12, a13 up to a1n, a21, a22, a23 up to a2n, down to a sub m1, a sub m2, a sub m3 up to a sub mn. This m by n matrix is called the coefficient matrix. We shall refer to this as the coefficient matrix. We next define matrix B as the m by 1 matrix consisting of the elements b1, b2 up to b sub m. And then our matrix X, which is an n by 1 matrix consisting of the unknowns x1, x2 up to x sub n. So clearly, this system of equation, which are going to denote by star, can be written as a product of matrices A and X equal to the matrix B. Alright, so let us check. First row of A, A11, A12 up to A1n, multiplied to the only column of X, X1, X2 up to Xn. So multiplying the first row of A to the only column of X will yield us the left equation, or the expression at the left of the first linear equation, and that is equal to b sub 1. The second row of A multiplied to X will give us the expression appearing at the left of the second equation equal to b sub 2. So we do that up to the last row of A multiplied to X, which will yield the left side of the mth equation of the system equal to b sub m. Alright, so Ax equal to b is a representation of the system of m equations in n unknowns. Again, we shall refer to matrix A as our coefficient matrix, Matrix B contains all the pure numbers found at the right side of each equation in the system, and matrix X is the matrix containing all the unknowns, x sub 1 up to x sub n. Let me now give you the procedures in finding the solution a system of linear equations using Gauss-Jordan reduction method. Okay, so the first step is to form the m by n coefficient matrix A, the m by 1 matrix B, and the n by 1 matrix A, or matrix X. Okay, then second, we form the m by n plus 1 augmented matrix A, B. So in other words, we will simply append the elements of matrix B to matrix A, thus making our augmented matrix an m by n plus 1 matrix. So we are adding one column to matrix A, and we shall refer to it as the augmented matrix AB. The third step is to transform the augmented matrix into a reduced row echelon form, which we're going to note by CD. Alright? Using elementary row operations. So first, the augmented matrix AB, we will reduce this to echelon form. And once we have done that, the next step is for each non-zero row of matrix CD, we solve the corresponding equation for the unknown associated with the leading entry in that row. Rows consisting entirely of zeros can be ignored. So the steps are quite simple. No? After forming the augmented matrix, you shall transform it into a reduced row echelon form CD. And then you are just going to rewrite the system of m linear equations in n unknowns using the matrix CD. So to illustrate, let us have an example. Solve the following system. So we have 2x plus 3y equal to 1, 3x minus 2y equal to 8, negative 2x plus y equal to negative 5. Alright? So first, let us define our coefficient matrix by plucking out all the coefficients of the unknowns 2, 3, 2x plus 3y. The coefficient of x is 2 and the coefficient of y is 3. So that forms the elements of the first row. Then 3, negative 2, negative 2, and 1. So our matrix A is a 3 by 2 matrix. 3 equations in 2 unknowns. Next, our matrix B consisting of the pure constants 1, 8, and negative 5. Then, matrix X consisting of the unknowns. There are only 2 unknowns, X and Y. Alright? So the augmented matrix A, B, we rewrite the elements of A, 2, 3, 3, negative 2, negative 2, 1. And then we append the elements of B, 1, 8, and negative 5. Right? We shall now reduce this to echelon form. So we can start with 2. So we can divide this by 2. That will be 1, 3 halves, and 1 half. Then we shall multiply this by negative 3. Negative 3 times 1 and 3 is 0. Negative 3 times 3 halves is negative 9 halves minus 2. That will give us negative 13 over 2. Then negative 3 times 1 half is negative 3 halves plus 8. That will be 16 minus 3. That will be 13 over 2. Okay? So 16 minus 3 is positive 13. Then, we need to turn negative 2 into a 0. So we shall multiply the first row by 2. 2 times 1 is 2 and negative 2 is 0. 2 times 3 halves, that will be 3. Plus 1 is 4. 2 times 1 half is 1. Minus 5 is negative 4. Okay? Next, we have to change this into a 1. So we will multiply it by negative 2 over 13. So 0 times negative 2 over 13 is 0. Negative 2 over 13 times negative 13 over 2, of course, is 1. And negative 2 over 13 times 13 over 2 is negative 1. Okay? Next, being a leading entry of the second row, the element along the second column above and below that leading entry must be a 0. So we need to change this into a 0. And to do that, we will multiply the second row by negative 3 halves. So 0 times negative 3 halves is 0 and 1 is 1. Negative 3 halves times 1 and positive 3 halves is 0. Negative 3 halves minus 1 is positive 3 halves. Okay? Positive 3 halves, and 1 half is 4 halves or 2. Okay? Then we need to make this 4. We have to turn it into a 0. So we multiply the second row by negative 4. So negative 4 times 0 is 0 and 0. Negative 4 times 1 is negative 4 plus 4 is 0. Negative 4 times negative 1 is positive 4. Minus 4 is 0. As you can see, this is already in the reduced row echelon form. So, we shall rewrite the system. This is actually the augmented matrix. So, the system corresponding to this will be 1, 0, 0, 1, 0, 0. Okay? That's supposed to be the matrix row equivalent to A. Alright? And then, the unknowns. What are the unknowns? The unknowns are X and Y. And that must equal the last column, 2, -1, and 0. Okay, let us perform ordinary multiplication to these two matrices, 1, 0, 0, 1, 0, 0 to xy. So first row multiplied to xy. What do we get? We'll be getting 1 times x plus 0 times y, right? Or simply x. We'll be getting x. 1 times x plus 0 times y, and that is equal to 2. Next, second row. Second row, multiply to xy, 0 times x, 1 times y. That gives us y. That gives us y equal to this one, -1. And then the third row consists entirely of zeros. Multiplied to xy. 0 times x, 0 times y is of course equal to 0. So 0 equal to 0. So therefore, let me clear this up. Alright. So therefore, our x is equal to 2 and y is equal to -1. Alright. Let us take on another example. Solve the following system. Say x plus 2y plus 3z equal to 9, 2x minus y plus c equal to 8, 3x minus c equal to 3. Okay, so this is our system. Let us form the augmented matrix AB. That will be the coefficients 1, 2, 3, 2, -1, 1, 3, 0, -1. And then we append the elements of B, which are 9, 8, and 3. So we shall transform this into reduced row echelon form. Okay? So 1, 2, 3, 9, 2, -1, 1, 8, 3, 0, -1, and 3. We rewrite the first row, 1, 2, 3, and 9. What do we multiply to the first row to make this element 0? We shall multiply it by -2. So -2 times 1 is -2 plus 2 is 0. -2 times 2 is -4 and -1 is -5. -2 times 3 is -6 and 1 is -5. -2 times 9 is -18 plus 8 is -10. Alright? How about this one? to make it a 0, we multiply this by negative 3. So multiply the first row by negative 3. Negative 3 times 1 is negative 3 plus 3 is 0. Negative 3 times 2 is negative 6, and 0 is negative 6. Negative 3 times 3 is negative 9, and negative 1 is negative 10. Negative 3 times 9 is negative 27, and 3 is negative 24. Okay? Next, we have to turn this into a leading entry. So we have to multiply it by negative 1/5. Alright? So we multiply this by negative 1/5. So 0, 1, 1, and 2. Okay? This is now a leading entry, and the elements above and below must be 0. So we multiply it first by negative 2. Negative 2 times 0 is 0 and 1. Negative 2 times 1, negative 2 plus 2 is 0. Negative 2 times 1 is negative 2, and 3 is positive 1. Negative 2 times 2 is negative 4, plus 9 is positive 5. Okay? Now, how about negative 6? We multiply this by positive 6. So 6 times 0, and 0 is 0. 6 times 1 is 6 minus 6 is 0. 6 and 1 is 6 minus 10 is negative 4. 6 times 2 is 12. Minus 24 is negative 12. Okay? Now, we go to the third row. We have to turn this into a 1. And to do that, we multiply it by negative 1/4. Multiply it by negative 1/4, or we simply divide by negative 4. Okay? So negative 1/4. So our third row now will be 0, 0, 1, and 3. Okay? Next, we need to turn these elements into zeros, right? So we shall multiply this by negative 1. Negative 1 times 0 is 0, and 1 is 1. Negative 1 times 0 is 0 and 0. Negative 1 times 1 is negative 1 plus 1 is 0. Negative 1 times 3 is negative 3 plus 5 is 2. We multiply the third row still by negative 1 to make this element 0. So negative 1 times 0 is 0 and 0. Negative 1 times 0 is 0 and 1. Negative 1 times 1 is negative 1 and 1, 0. And finally, negative 1 times 3 is negative 3, plus 2 is negative 1. Okay? So this is now in the reduced row echelon form. So we shall rewrite our system. 1, 0, 0, 0, 1, 0, 0, 0, 1, multiplied to the unknowns. X, Y, and Z must equal the last column, 2, negative 1, and 3. Okay? So, first row is multiplied to X, Y, Z. 1 times X, 0 times Y, 0 times Z is of course just X. And that is equal to 2. Then, second row, multiplied again to X, Y, Z. 0 times X, 1 times Y, 0 times Z will give us Y. And that is equal to negative 1. Finally, Third row multiplied to x, y, z. 0 times x, 0 times y, 1 times c will just give us z equal to 3. So our x is 2, our y is negative 1, and c equal to 3. Okay? Now, the Gauss-Jordan reduction method is actually an improvement of the so-called Gaussian method, or Gaussian elimination, or Gaussian method. Now, in the Gaussian method, the first two steps are the same, no? Form the augmented matrix A, B. Then, transform this augmented matrix B into either an upper or a lower triangular matrix. Alright? So not necessarily a reduced row echelon form, but either an upper or a lower triangular matrix. And then finally, you rewrite, let us call this as C, D. Then rewrite the system using the above matrix and solve for the unknowns using back substitution for the upper triangular matrix or forward substitution. So rewrite the system using the above matrix and we solve for the unknowns using back or forward substitution. Okay? So we will not transform the augmented matrix into a reduced row echelon form. We will simply transform it into either an upper or a lower triangular matrix. We write the system corresponding to the above matrix C augmented D, and we shall use either back substitution or forward substitution. So let us have an example. Solve the following system using Gaussian method. So x minus 2y plus c equal to 4, 3y plus c equal to negative 2, 2x plus 3y equal to negative 1. Alright, so we form the augmented matrix 1, negative 2, 1, 4, 0, 3, 1, negative 2, 2, 3, 0, negative 1. Since this is already a 1, actually, it's not really necessary that your leading entry is a 1. No? So, if this is 2, you can retain that entry as 2 without converting it into a leading entry. So, since it's a 1, let us just rewrite 1, negative 2, 1, and 4. Since the entry below is already a 0, we also rewrite the second row 0, 3, 1, and negative 2. Now, for This entry, to become 0, we multiply the first row by negative 2. So multiply the first row by negative 2 and add it to row 3. Thus, we will be getting 0. Negative 2 times negative 2 is positive 4 and 3 is 7. Negative 2 times 1 is negative 2 and 0 is negative 2. Negative 2 times 4 is negative 8 and negative 1 is negative 9. Okay? Then, this one, a 3, will be changed into a leading entry. No? Or, if you wish, you can retain the 3 and you just multiply this by negative 7/3 and add it to the third row. Okay, you can do that. If you don't want to change this into a leading entry or a leading one, you can simply multiply this by negative 7/3 and then add it to row 3 to make it a 0. But it will be, there will be ease in our solution if we'll just turn it into a leading entry or a leading one. So we multiply this by 1/3. So we'll be getting 0, 1, 1/3, and negative 2/3. Okay? The entry above this leading entry along the second column should be 0. So I'm referring to the entry negative 2. So we have to turn that into a 0. So we multiply this by positive 2. So 2 times 0 is 0 and 1 is 1. 2 times 1 is positive 2 minus 2 is of course 0. Then 2 times 1/3 is how much? Sorry. There is no need, since we are using the Gaussian method, there is no need of making the element above 0. So I'm sorry about that. I will simply retain the element or the first row. No? Because after all, we're just after an upper triangular matrix. So sorry about that. So 1, negative 2, 1, and 4. I just have to make this entry equal to 0. So I shall be multiplying this by negative 7. Okay? So negative 7 times 0 is 0 and 0 is 0. Negative 7 times 1 is negative 7 plus 7 is 0. Negative 7 times 1/3 is negative 7/3. And negative 2, that gives me negative 13 over 3. Okay? Negative 13 over 3. Then negative 7 times negative 2 over 3 is positive 14 over 3 added to negative 9. So that will be 14 minus 27 is negative 13 over 3. Okay? So the idea here, no, our aim is to transform this matrix into an upper triangular matrix. That is why the entry above the leading one in the second row, in the second column, no, we did not turn the entry above that leading entry into 0. Just the entries below. And there is only one, no? There is only one entry below that leading entry. Okay? So, next, for the third row, we multiply this by negative 3 over 13. Negative 3 over 13. In order to turn it into a 1. No? So 0, 0, 1. And then this is also equal to 1. So let me rewrite the first two rows. Okay. So this is now an upper triangular matrix. No? It's an upper triangular matrix there. Actually, it's the first three columns. This one. There. It's an upper triangular matrix. So what is the next step? We will write the system corresponding to this matrix. So let us block out the first three columns. 1, -2, 1, 0, 1, 1/3, 0, 0, 1. Multiplied to the unknowns. Our unknowns are x, y, and z. And that must equal the last column 4, -2/3, and 1. So we shall rewrite the system. We multiply the first row to the only column of the unknowns, x, y, and z. So we'll be getting 1x minus 2y plus c. Okay? That will be x minus 2y plus c equal to 4. Then, second row. Second row, multiply to x, y, z. What do we get? 0 times x is 0. 1 times y is y. Okay, y. And then 1/3 times c. So plus 1/3 c equal to -2/3. Then the third row. The third row is multiplied to x, y, z. 0x, 0y, 1 times c. So that is just z equal to 1. At this point, we're going to apply back substitution. Apply back substitution. So since c is equal to 1, we substitute this value to c in the equation above. So we'll be getting y plus 1/3 times 1 equal to -2/3. So it gives us the value of y equal to -1/3 and -2/3, -1. Okay? Then, we will substitute c equal to 1 in the first equation, y equal to -1 also in the first equation to find the value of x. So, let us do just that. X minus 2 times, what is the y value? -1 plus c, which is equal to 1, equal to 4. So x plus 2 plus 1 equal to 4. That gives me the value of x equal to 1. Okay, so what did we do here? The augmented matrix is transformed into a triangular matrix, either upper or lower. If you chose to use an upper triangular matrix, we rewrite the system corresponding to this and apply back substitution. If we opt to use a lower triangular matrix, you are going to use forward substitution. Okay?